when you have lots of data, try to figure out what that lots of data is trying to tell you rather than picking up a piece of that data and analyzing it for a specific problem. There's an opportunity when we have lots of data with many, many variables and long time series. And what we need to do is try and glean out more from that data set rather than just saying, okay, I'm analyzing a small piece and I just need a few variables in that analysis. Just telling a friend of mine that I'm in Alabama, and she texted me saying, hey, remember, it's 20 years since Katrina to the day. So I think it's important to acknowledge the impact of Katrina and what the lessons we have learned. And I think was it 3 years ago or 4 years ago, Aida went through the same path exactly on the same date, and the impact was minimal. We don't even remember Aida. And that was because we learned from the previous episode and we took care of things so that that impact doesn't happen again. And I think that context is important because the way we address problems, we need to visit the way we think about problems. And so it is in this context that I'm going to talk about things today. And but first of all, before I do that, I'm not going to individually acknowledge a lot of my students, but all of our faculty. We know that a lot of the stuff that we present is based on the work we do with our students and postdoc. And that would not be possible. I mean, there will be mentions of names as we go along, but I do want to say that what I'm going to present is a collaborative effort with a lot of people that I have worked with over the years. So it's a trivial thing to say that it's an era of data-driven science, right? I mean, so when a data set is sufficiently rich, it transcends mere numbers, becoming a living repository of every insight we might otherwise painstakingly extract through fragmented analysis. The bottom line is, how do we maximally utilize our data sets to understand the thing? I mean, this particular picture is essentially depicting that we are putting sensors all over the place, right? And so when we study our environment, natural, human-made, or whatever, what opportunities exist in actually maximally utilizing this data? A few decades ago, I think this is a 1972 paper. It's a foundational paper. More is different. Okay, so let's take a moment to ponder that concept. The more we have, if we continue to think about that stuff in the traditional way, we are losing a large opportunity to unravel stuff. So when we think about data in any context right now, there is a lot. And when you think about earth science data, we have data from NASA and NOAA and USGS and EPA and all those places. And yet, when you talk to hydrologists, they will come and say, we don't have enough data. And my response is, are you using all the stuff that you have? You will not have data in your backyard, but are you using that? So a richly detailed data set behaves like a complex system in which novel, emergent, informational patterns reside. Properties we cannot predict simply by drilling deeper into individual measurements. In other words, when data attains sufficient informational complexity, they themselves break the reductionist view. And how do we even start to think about that, right? So we all think about complex systems. A rich data set is a complex system. We need to be able to think about how we uh, extract information. So, and how to use it. So, what I'm going to talk about is the concept of information from an analytical to predictive insights. So, I'm going to cover what is information, and I'm going to say that information is physical, so bear with me. Uh, Information flow is a concept that we developed in our group. Then we'll go to causal interaction and generative AI, ML. That's the general structure of what I'm going to be talking about. So let's start with the problem of probing a complex system. We all know that a brain is a complex system. And this is a way we think about understanding the brain. We can put sensors all around, and what we can do is generate a whole bunch of signals. And none of them is flat. These are variations. And so this allows us to probe a complex system. And with this, we can understand the dynamics. We can understand coherence and breakdowns. We can map functions to local structures, that this happens in this part of the brain and this happens in this part of the brains, to the extent that there was a study, a New York Times article, which basically says we can take these signals and we can actually decode it.
The proof that you are seeking is available in books.
The proof that you are seeking is not available in books.
The proof that you are seeking is available in books. Shipbuilding is a fascinating process.
Shipbuilding is a most fascinating process.
Okay, so there are a few more examples. The point is that we can take these signals from the brain and actually convert it into a coherent thing that we can understand. When we are looking at a natural environment, we are in a position to actually do the same kind of a probing in a much more detailed manner. This is from one of my flux towers. That's on the left-hand side in the figure there. And we are measuring a whole bunch of different variables. You see this signal varying all over. Most of us will then gravitate to saying there is uncertainty. Okay, heck no. There is variability. That doesn't always translate to uncertainty. That's number one. The second thing is we are probing this, and how do we take all of this together and make sense? A lot of us will take a piece of this, maybe 3 variables, 5 variables, we analyze it. What is the evapotranspiration doing, or what something else is doing? Most of us don't go on to say, I want to maximally use this data set. So what the new data that is becoming available, more is different, is telling us to figure out how to basically use maximally this data set, right? And this data set contains information. Information is encoded in patterns of fluctuation, okay? When you write something on the board, you're creating a fluctuation between black and white or color or whatever, and that is all communicating information. If it was all white, there would be no information communicated. When I'm speaking, I'm creating a fluctuation that is creating the wave that is hitting your eardrums. If I did not communicate that, you will not hear me, right? So that is the key thing. Those fluctuations are not uncertainty, they are carrying information, right? And those fluctuations are causes and consequences of interaction. They are not happening randomly. These variables are dependent on each other. They are informing each other on a continuous basis. So we need to figure out how do we even think about this thing before we can use all the data. So we'll go back to the basics. What is information? Most of us would think that information is statistical stuff. We just quantify it. What I'm going to argue for the next few minutes is information is a physical quantity. Okay, so what does that mean? In the 1871, there was a book that came out by James Clerk Maxwell, Theory of Heat. Where he basically laid out the concept of is as a thought experiment of a Maxwell's demon. How many of you have heard of it? Nobody. One. Okay. The key is this. You have a chamber. There are a lot of molecules bouncing around in there, and it's in equilibrium, right? So now imagine if there was a demon which knew the velocities with which these molecules are moving. And this demon opened a trapdoor when a high velocity molecule came in to let it into a chamber, and a frictionless trapdoor. And so what will happen is, with that information, the demon can create an energy gradient. Okay? High energy molecules on one side, low energy on the other side. Notice what has happened. The information about the molecule velocity is fundamentally different from the velocity itself. Okay, that chamber still contains the same amount of energy. But what this demon is able to do is create an energy gradient, and therefore you can extract work. So the knowledge about the velocity is different from velocity, and hence the information is different from the kinetic energy, but nevertheless you can use it to do work by creating that gradient. Okay, so so it's important to know, acknowledge the knowledge of velocities is a fundamentally different attribute than the velocities themselves, and it can be used to create an energy gradient and therefore work, and so it has to be fundamentally different. But it has to be a physical quantity because you can trace it, translate it into doing work. So this is the key. It's a fundamental physical quantity. Based off of that, Szilard in 1929 came up with this idea, says, okay, I'm going to consider one molecule in a chamber, one single molecule, okay? And I'm going to partition it with a frictionless surface, and then I'm going to figure out where is that molecule, which half. And depending on whether it's in the right half or the left half, you can get it to do work. If the molecule is in this half, it's a frictionless surface, it can move around, it has energy, and therefore it can do some work, right? And he quantified the amount of work, which is Boltzmann constant times temperature times log of 2. Okay, so now what you have done is taken information and converted it into a quantity of work. Okay, again, this is a thought experiment, nothing physical. So what is it? This is the work associated with a binary decision process. Yes, no. Is it in this half? If the answer is yes, it will do work in the other direction. If it's in the other half, it will do work in the other direction. It's a binary decision process. And it's also associated with the amount of entropy, right? So the key is that this is the first clear link between information and then quantifying how much energy is associated with this. So this is one bit of information. The term bit was coined later in 1946, but now you can basically say that this amount of information is associated with this much energy. Okay? So this has served as a foundation for information theory. It was a thought experiment, but it has been physically realized. So this is a paper from 2010, experimental demonstration of information to energy conversion. So energy to information, you guys know examples of energy to information? No? Anybody use computer? All your information stored on computer, it uses energy. That's trivial. Information to energy on a net basis is non-trivial, right? So there are others, experimental realization of Szilard engine with a single electron. So measurements to basically information and memory is the foundation for information physics, cybernetics, computing, and there is an intimate connection between entropy, which is a system property, and information. And we think of this as an observer property. And I'm going to challenge that notion in just a second. But nevertheless, the way we think about information, we think about human interpretation of that in there. So this is another one, on-chip Maxwell's demon as an information-powered refrigerator. So basically saying that information can, on the net, produce energy, which is important. Photonic Maxwell's demon. These are all very recent papers in the last decade. Right? So things from about 80, 90, 100 years ago, which were thought experiments, are being realized. And the key is to start thinking about information not as a statistical measure, but the statistical measure representing a physical quantity. Okay? So a lot of people talk about physics-informed machine learning, and the idea in physics-informed machine learning is we are dealing with mass, momentum, and energy. There is a fourth dimension. I think information should be part of physics in the informed machine learning. So what Shannon did was he basically developed a whole new paradigm saying, okay, information is related to amount of surprise. So remember that fluctuation. If you had a flat signal, you would have no surprise and hence no information. But if you have variation, you have a surprise because it's varying and therefore you have information. Okay, so that, so the more variation you have, the more information you will have. So it's inversely proportional to the probability of something happening. There are certain other properties that sums of two independent events should be sum of each, and it's a continuous function. Eventually, the bottom line is this is the informational measure of entropy. Okay, so this is the average information which we call information entropy, right? It's related to physical entropy. We won't get into that, but nevertheless, average over a probability distribution function. So I won't go into too much detail except that we can say entropy is a probability of any probability distribution. It can be regarded as a measure of ignorance because you're being surprised when something happens because of variation. So you can think about the physical versus the surprise as duality. I'm going to hammer this a little bit more. So a lot of the physics world has been debating this problem for a while, for a few decades now. And so Wheeler and Ford, they published this beautiful characterization, it from bit, rethinking the nature of universe. So we think bit represents it, right? Because it's about information about something. But what if that something is coming out of informational? So the traditional physics we think about is mathematics, physics, and information. Quantum mechanics thinks differently, information to laws of physics and matter. And they would argue that laws of physics is actually an aggregation of information. So the key is there, because each bit mapped by Szilard, we know what that energy is, we can treat laws of physics as informational statements and not bookkeeping, which is what the statistics will do. And so energy budgets and everything are encoded in informational budgets. Seth Lloyd is one of the pioneers on quantum computing. And so he says, well, if that's the case, the universe is computing. And what is the computational power? And whether you agree with the number or not, whether it's 10 to the power 120 bits of information in the universe or not, the fact is that that notion that there is something physical associated in information is important. And I'm going to not belabor this point. But so what is this bias beyond what we know as laws of physics? The laws of physics do not explain complexity. So if you look at the world around you, there are so many interactions happening because the hurricanes, the weather, whatever emerges is a result of interaction. If you measure a single variable, it's not going to tell you the whole story. If you measure 2, 3, 4 variables, it's not going to tell you the whole story. So to understand nature, because be it science, be it engineering, we are essentially managing nature. We are trying to understand. We are trying to do things. And oftentimes we are just crashing, right? Either immediately or years or decades down the line. Our idea is that we need to think about how this interaction is happening to generate the processes which we are trying to respond to. And we don't explain complexity, right? So, but the universe is. So the key here is that the only way to generate complexity is through simulations. Okay, you need informational dynamics, which you can't do with the laws of mass, momentum, and energy characterization. So I think we are at the beginning of this kind of analysis. And so I'm going to move on to the next step, which is information flow. I call it a new lens for system dynamics. And so this is done by one of my students, Allison. And take a simple example. You're looking at the Earth's surface. You have the plants, you have the atmosphere with humidity, you have the solar radiation, you have rainfall, wind, you have fluxes of heat, surface wetness. There is a complex interaction happening between them. I've been in the field, and we were measuring leaf temperature with a thermal camera. And we block the light, and immediately the leaf temperature starts to drop. Okay? What does that do? That results in change in the amount of photosynthesis. It results in a change in amount of CO2 uptake and the release of water vapor, and therefore the heat holding capacity of the air, and therefore the temperature and so forth. It happens very, very quickly. If you're measuring all these variables, you will see this dependence with just maybe a brief delay, just very. But if you miss out that on resolution, or you miss out on how many variables you are analyzing, you're going to miss out on the interaction. So if you change one, in this case radiation, or you change anything, it's going to propagate. So that very complex set of signals that I showed you is reflecting all the change. When a cloud passes over the surface of the earth, it's changing. The temperature is changing, the evaporation from the soil and so forth. And it is continuously changing. So the question is, how do we even think about perturbation in one variable affecting perturbation in another, or creating perturbation in another, right? And it's not like one-way process, it's feedback, right? So there have been existing notions. So Granger causality, which was developed actually in the 1960s, says that, well, if I'm trying to predict one variable, and if I know I can predict based on its history, but if another variable adds more predictability, then I can say that there is a causal influence from that variable, right? So I'm increasing the predictability. And so pole causality is a slightly different notion. It says basically if I can intervene and then prove that that intervention into one variable has affected something else, that notion comes into play. Transfer entropy was developed a little later, and it's an extension of Granger causality, but from a probability distribution function. And it generalizes beyond a linear system behavior. So the transfer entropy is identical to Granger causality for linear dependencies between Gaussian variables. But this is a very, very important development. If you look at how many places this concept is used, it's enormous. Okay, because for the first time it says, okay, I can take the idea of causality between two variables. Let's keep that very clear. In this case, x and y, says I can now say how the past of x brings in more knowledge about y than the past of y alone cannot do it. Okay, and that additional thing is what is transfer entropy. And so I'm going to skip this, but so think about this. You have a variable z, and it has a certain amount of variability, and hence if you're trying to predict it, you're going to be off a little. There is a probability distribution function associated with it. And then you take its history, and then you can reduce its predictive uncertainty. But if you take a history of another variable, then you can reduce it even more. And if that happens, that additional reduction is what is transfer entropy. Okay, that's in a nutshell what transfer entropy is. Right. So we were working with with one of my former students. This is 20 years ago. Ben Ruddle is a professor in Arizona right now, and we started applying this transfer entropy with the full cognizance that when we are looking at a statistical measure, it's actually about something. Okay, something physical. It's not arbitrary. Okay, it's not just mathematical stuff. Okay, and we analyzed how this interaction. We took every pair of those variables, and what we found is we can see the interaction. We can see this transfer entropy flowing from one variable to other. And so the left-hand side is the first one we saw, and well, we got excited about it because this makes sense. There is interaction in the atmospheric boundary layer, there is turbulence structure, there is ecological structure, and there is synoptic influence that we could see. It's like, okay, what if all systems behave this way? So we took another data set from a drought, and what we found is essentially there is a decoupling between the atmospheric processes and ecological processes. So the way that feedback mechanism works, remember, we are not using any equations here. Okay? This is not synthetic data. This is actual observed data. And we can see the decoupling. So there are potentially many different regimes of such interactions that come about when we think about how to characterize these dynamical systems by looking at large data sets. And so these analyses reveal internal dependencies between components of a complex system. We can identify propagation of fluctuations between variables to expose dynamical connectivity. They reveal coherent subsystem and sub-network organization associated with different functional modalities. And they reveal different functional modalities, stressed, unstressed system. Remember the picture of brain I showed you? Exactly the same kind of properties. Okay, so this is exciting. So with Ben, when we started working on the paper and so we submitted it, I said, no one is going to appreciate what the heck we are talking about. Okay, this is going to come out and be rejected and we'll have to iterate. Surprise, surprise. The reviewers were actually very positive about this thinking. And so we were encouraged in there. I welcome you to explore this. And then a few years later, I was working with another student, Alison Goodwill. What happened, what motivated this work is in 2010, there was a paper by Williams and Beer. It wasn't published in a peer-reviewed article, it was published in Archive. And what they said is, okay, forget the two-variable interaction, let's do a three-variable interaction. Okay, so you have source 1, xs1, and source 2, xs2, which are informing a target variable. So what kind of influence we can have? We can have unique information flowing from source 1 to target, unique information flowing from source 2 to target. There could be some redundant information, and there could be some synergistic information. And the way to think about it is, if I sit down with somebody and work on some ideas, I'll bring in something unique, the other person brings in something unique. We probably have the same math and science background, so we have redundant content. But then because we sit down and talk together, we create something new. That's synergistic. So those are your 4 possibilities, right? So what Williams and Beer did is laid this equation out. And so those are your unique, redundant, and synergistic. And that's that interaction space between the sources and the targets. And so we said, okay, let's analyze this. So it's the same set of variables that I showed you before. We have 1 minute data. and said, okay, can we figure out how air temperature and wind speed influences relative humidity together? Okay, this is what the data looks like. Can you figure out any structure to it? Heck no, right? So visually makes no sense. But we partition it into windows and we said, okay, can we compute this thing? Now, we are doing everything in our powers to make sure that these are statistically significant results. Okay, so what we see is that the contributions of unique information from air temperature, from wind speed, the redundant and synergistic, they change within a course of a day and across days, right? So you go from unique information, which is essentially air temperature determining the relative humidity, to more complex interactions, to even more complex interactions in there. So the synergy starts to rear its head up and you start to get more contributions in there. So from this, just two variables influencing a third, we can do this all across. So instead of pairwise, we can do this all across. And what we have is, okay, during the nighttime, the feedback information is different from the daytime, that your black arrows at the top. But we can parse it out. So if you look at the right, this side of this, we can basically figure out what are the sources of information, which are the targets of information, how much is flowing. The wider those strips are, the more information that is flowing. And then we can create this feedback diagrams at the bottom. And what we see is that a wet and a rainy period induces a lot more feedback. Well, we say, yeah, big deal. That's obvious. But we haven't quantified that ever, right? Dry period is useless in terms of creating feedback. So water is an essential mechanism for creating feedbacks between the land and the atmospheric system. Yeah. So we publish a whole bunch of papers. You're welcome to look at it. There's a lot more depth to it. I'm covering more breadth here. So obviously there is fluctuation and causal influences happening. And so we need to think about how to capture this interdependency better. So remember, when I said 3 variables, there are 4 possibilities. You go to 4 variables, and there are 18 possibilities. We call this the flower diagram. Trying to estimate every piece of this is a nightmare, statistically, in there. So we needed to solve this problem, right? Because I said more is better, but if you can't actually estimate things with a lot of variables, it's going to be problematic. So one way to think about it is basically, let's take an example of a 4 variable problem. We can represent this as what we call it a process network. So an arrow onto itself is a self-feedback, and an arrow onto another variable is one variable influencing another. The numbers are the time step, lag time step at which these are influencing. So this we can do with the previous approach, but we can then unfold this and basically make it march in time. This is what is called directed acyclic graph. Okay, so we can basically figure out U is influencing these variables at this time and so forth, right? So this is a cause effect influence forward in time. Okay, so for causality, there is a precondition. It's a symmetry breaking concept. It basically says past affects the future, future doesn't affect the past. You do correlation, you do mutual information, it's not a symmetry breaking measure. And therefore, you cannot figure out causality. I'm going to say the following. Just because it's symmetry breaking doesn't mean causal. Okay, so this is a necessary condition, but not a sufficient condition. But I haven't seen anybody figure out what the sufficient condition is yet in the literature. So any of you smart people can do that. That will be so awesome. That's an open problem. But absent that, we will say, okay, if the necessary condition is met, there is a potential for causal influence to happen. So the key here is that if there is a perturbation at any moment in time, how does it propagate forward to another variable to create another perturbation? Okay, so now you have data points. Can you figure this out? Okay, so and then what you can do is think about that black point and say, how is this entire history figuring this out? So there was a beautiful paper by Runge, and they used conditional probability distributions and figured out the influence of that red to black. Okay, conditional upon everything else. So just that, they called it the momentary information transfer. And that was a brilliant mathematical analysis or a framework. And so from that, Pishi, raise your hand. He's a faculty here. He figured out how to, actually no, this one still, Runge did this to then move it forward, and then Pishi did, okay, so if you have a red and you have a blue, how do those two interact to create that black? Okay, so remember the three variable problem? We know how to solve three variable problems. So what we have done is essentially taken that three variable capability and then said, okay, how do we march it forward in time? Okay, that was Pishi's work. And then once we figured that out, we said, okay, now we can figure the whole thing out. Okay, so we could figure the math out in there. And so now we know how the interactions across multiple variables, and I don't think there is a limit except the data being a limit in the statistical computing, but not the mathematical formulation, how these things can influence this thing forward. So with Pishi, what we took the stream chemistry data. This is a 7-hourly stream chemistry data in UK. We're looking for some data set. Okay, and it has been shown to have a fractal signature. Okay, so no matter how much detail you go, there is details. That's the definition of fractal. And each variable has been analyzed independently and established that, except for the last one, I think all of them have a fractal signature. Nobody asks, why is it fractal? Where does the fractality in this come from? You can put in statistical models for long memory reproduction of these properties, but what is creating this fractality, right? So that's an important question to be answered. So what we were able to do, just to get into deeper analysis, is said, okay, if a whole bunch of variables is affecting that black dot, which is the target, we were able to break this into immediate causal history and a distant causal history as a function of tau, which is the measure of the immediate, and we can vary the tau. So we can vary tau to very long or to very short, right? So we can figure out how is this immediate information decaying as we move this tau further out. And if you have a long memory process, it should decay with a power law. But if you have short memory, it should decay out exponentially, right? So we did all that analysis. We came up with formulation. Pishi would remember the agonizing hours in this thing. And so I won't go into the details of it. And then we can figure out the self-dependency, how z of t is dependent on its own memory history, cross-dependency within the recent dynamics and within the further out distant dynamics. And so we won't go through this. So you can create pretty complex dependencies. Okay, and then we can analyze this and say, okay, how can we get a large number of signals to figure out a behavior of various variables? And so again, we won't go through the details, but what happened is we analyzed this thing and we looked at this analysis and we saw that there is a coherent pattern of these interactions. Okay, and so there are certain variables which show one kind of a pattern of interaction in terms of synergistic, redundant, unique dynamics, and between uh, the variable and everything else, and within the past and the near immediate and distant dynamics, and they behave differently depending on where the origin is, because this has oceanic influence in terms of the sodium chloride, and we can see that there are aluminum is a terrestrial origin, and then there is a combination. They show different patterns, but we didn't impose it. We are interpreting it, okay, because we need to make sense out of this. And so the key story is that what, and Pishi will disagree on what I'm going to say, but I'm going to say it, is that the interaction between these variables is actually creating the fractality in there. Where does the memory reside? Memory doesn't reside in own history. It is basically residing in all the interactions that are happening, right? And so that is showing up over a very long period of time. So when we are thinking about memory, almost always we are essentially 5 minutes. I got 15, man. So it's important to know that. Okay, so we publish all this stuff, and so I should skip that, but basically what I was able to show is that I can create actually mathematical equations for the evolution of information flow. Okay, so information flow as a concept in a dynamical system. As the dynamical system is evolving, there is information flow. Welcome to read about it. So this brings us to generative dynamic, modern world of AI machine learning. And so when we are trying to predict a variable's future, could we exploit this dependency knowledge? Instead of just giving everything to AI, machine learning stuff, we wanted to figure out. So we did some analysis with information flow, but the bottom line is this. Some people call it the suitcase diagram, which is just fine with me. We found out that the flow Q can be used to predict calcium ions. The flow in calcium can predict magnesium ions, and the Q, Ca, and magnesium can help predict sodium ion better than just using Q and sodium, and so forth. So this is a dependency diagram which we fed to an LSTM model, but the standard LSTM did a great job, except that we could do better. And so we modified LSTM. I won't go through the details of this, to capture some other properties. And as a result, what you see is the red line is the training, and everything beyond is the testing. Go to the look at the this diagram here. The orange is the standard, and the blue is this modification to the LSTM that we are trying to do. And it does a better prediction. Not, I mean, we won't capture every nuanced variation, but it does much better. So I'm going to skip this. Okay. So the next stage, I mean, which everybody is familiar with using transformers, we had said, okay, now if you have a whole bunch of very high frequency variables, 10 hertz, right, 10 measurements per second. And so can we get these models to predict these high frequency variables? And also look at the third one, which is the temperature. The blue is the training set, the orange is the testing set. The orange, the distribution is an out of distribution prediction problem, right? If you run a standard transformer, it doesn't do great. There is somewhere a complex dependency built into these variables. You see these blobs, they are cross variations. We don't see it. Our eyes don't see it. But you feed it to a transformer model, and there it is. So you see that orange. On the other one, you don't see blue because right underneath the orange. Okay, we are able to predict out of distribution properties with the kind of modifications that we are doing. And we are predicting so much variation in there. A lot of the times, if you just use very simple models, this will be cast as noise. Think about the following. often, I mean, if you're trying to predict this at a point, you're going to not succeed because trying to do with any direct simulation is not going to work. So the question is, do machines learn dynamics? Okay, what's our hypothesis? In a multivariate dynamical system, fluctuations propagate causal influence. An AI model boosts forecast accuracy when their compressed internal representations faithfully encode these propagation pathways through informational modes. The richer this preserved structure, the more causally aligned and operationally predictive the model becomes. So information flow through fluctuation, we know, fluctuation propagation, I made a case for that, and the causal interaction. That leads to the multivariate time series that we have. The best way to predict is to take that information dependencies and put it in a model. And the reason I believe some of the AI models do better is they capture that dependency far better than any of our physical equations do. Because the physical equations we use, they were formulated in a lab. What do we do in a lab? If there are 5 degrees of freedom, we suppress 3 and maybe leave 2 degrees of freedom open, and we say, okay, this is a great governing equation. And then we get these equations to talk to each other as if those 3 constraints didn't exist. Whereas in the data, they don't have any suppressed degrees of freedom. They are capturing the entire dynamic. So when we are feeding them through our systems, it is essentially somehow capturing those dynamics. We need to figure those things out. So from demons to decisions, energy information learning converge. Entropy harness, we talked about that. So like Maxwell's demon, modern generative models turn raw fluctuations into useful gradients. And only now the gradient has predictive power for Earth system science. Emergent properties, information flow lenses ensures that gradient follows causal channels, not noise, that are responsible for self-organized structures and associated functions, and embedding these frameworks into decision platform, prediction, whatever, will hopefully help us. So I'll close with this. In a data-rich world, the future belongs to AI systems. They are very similar to demons. We can trust, and that trust is earned when their bits adequately capture information flow among interacting variables. Thank you very much.